Okay, let's get started. Sorry for running a little bit late. So in the last lecture, we have introduced how do we conduct stochastic subgradient descent for training SVM, right? So basically, we know that we can calculate gradient and apply gradient descent, but for large data scenarios, like you have like 10,000, you have hundreds of thousands or billions of training examples, you have to pass through the entire training data set to calculate one gradient. That is pretty inefficient. So in practice, people always prefer stochastic gradient descent. Stochastic gradient descent means that, okay, every time I just, when I look at one example, I just use that example to fake a data set, right? And then calculate the loss on that fake data set. I use that as an approximation of the gradient. Such a gradient approximation is called stochastic gradient, right? There's some like a nice theoretical justification for this, right? So yeah. So basically, we can show that the original training loss, which is on the entire data set, can be viewed as an expectation of this so-called stochastic gradient. So that's why we should, like every time when we random sample one example, we duplicate our examples to fake a data set. That data set should have the same number of examples to as the original data set. And only in this way, you can show that the gradient of the faked data set, the gradient of the loss on the faked data set is an unbiased estimate of the true gradient, right? And then there's like a rigorous theorem showing that, okay, if you update your model with this unbiased gradient estimate, then it guarantees the convergence to some function optimum, right? So, and then we can leverage this procedure to efficiently update our support vector machines model, right? And the only thing remaining is that we will calculate the gradient of SVM objective. We found that the loss function actually is not differentiable. The reason is because you have this hinge loss, right? So remember, the hinge loss is maximum between 0 and 1 minus function margin here. So actually, it doesn't have any rigorous definition of the gradient. So to address that problem, we introduced the concept called subgradient, right? So the subgradient means that, okay, for example, at this point, right? At this point, you don't have the gradient, right? But if you can find any line which is passing through this point, but lies below the entire objective function, then the slope of that line is called the subgradient. Right? It is a generalization of the gradient in the convex function. Right? For example, this figure. At this point, at x1, we know that at x1, the function f is differentiable. So I can calculate the gradient and I can form a tangent. I form a tangent line passing through this point, right? So the gradient, the slope of this tangent line is the gradient of the function at this point, right? But if you look at the point x2, actually, there's no definition for gradient here. Right? You won't be able to calculate the gradient of f at x2. But how do we update our model? If our model happens to stay here, how do we update our model at x2? Right? So we seek for the so-called subgradient. But subgradient, how is subgradient obtained? Consider like at this point, you can draw many lines, right? And there are like this line, this first dashed line, the second dashed line, all those dashed lines, they can pass through x2, but the whole line will stay below the entire function body. Then we define the slope of such a line as the so-called subgradient. Right? We can use subgradient to perform update. There's no influence on the convergence guarantees and so on. So based on this idea, we choose the subgradient for the SVM objective function, right? So here, because the hinge loss is typical, is a max function, is a max between 0, which is constant function, and a linear function, right? So the only thing we need to worry about is the gradient at this point, right? This turning point don't have any gradient, right? So I want to calculate some subgradient. So the idea is very simple. I just choose two cases, right? For example, if your position is here, right? I'm gonna just choose this constant function, right? Which is definitely a stay below the entire function body with 0 gradient, right? If I'm at here, right? I'm gonna choose this one, right? I'm gonna choose this line, which pass through the turning point, but stay below the entire function body. So I choose that slope as my subgradient. And you can easily merge them together to get a subgradient. And eventually, we just substitute this subgradient into our update of the SVM model in the stochastic gradient descent framework. We got our stochastic subgradient descent for SVM. So then we talk about, okay, to ensure the convergence, right? We will also need to set appropriate schedule of this learning rate or step size gamma t. So we give some sufficient conditions that guarantees convergence. That is, your sum square of the step size over t from over t to 1 to infinity is not infinite, right? And sum of step sizes from t equals to 1 to infinity is infinite, right? So basically, it means that your step size cannot be too large, cannot be too small. Right? Cannot be too large means that if it is too large, you're gonna oscillate forever and ever. You will never reach a minimum. But if it's too small, you probably just update so slow such that you will never be able to reach the value. So that's basically what these two conditions mean. And here we give some like a classical choice of the gamma t schedule, but we have to emphasize that in modern machine learning libraries, we have much more complicated mechanism to update gamma t. Okay, so some insight about the stochastic gradient descent. So if you want to look at the theoretical guarantees about the convergence, right? If, for example, one asks how many iterations do we need to get an accuracy within epsilon? So basically, if right, if this is our optimal, right, x star, right, and I would like to know, okay, within this epsilon distance from x star, right, how many iterations do we need? If you are optimizing a strongly convex function and your training examples, you have n training examples and your input dimension is d, you run gradient descent, the number of training examples you need to get accuracy within epsilon is this man. It's n times d times logarithm 1 over epsilon. So now we can see the problem, right? The limitation or restriction from the gradient descent. The number of iterations is determined by the number of training examples. That's why in the large data scenario, like you have 1 billion examples, you're going to run many updates or iterations. However, if you use stochastic gradient descent, the number of iterations to get to the accuracy with epsilon is proportional to d over epsilon. So you see that actually the convergence of the stochastic gradient descent does not rely on the number of training examples. So that's the amazing property, especially in the context of big data. Okay. So that's why, as we mentioned in the last lecture, right, it could be, you could see some weird situation that even you haven't been able to pass the entire training data for once, your algorithm has already converged. Why? Because the number of iterations for convergence is independent to the number of training examples you use. Of course, in practice, you probably still want to pass through the entire data set for multiple times, but imagine that every time when you see one example, you perform one update, right? So you pass through the data set several epochs, you have a updated model many times as compared to standard gradient descent. That's why in a large data scenario, stochastic gradient descent is always a more favorable choice. Okay, any questions so far? Well, just a quick review of what we have discussed last lecture. The update. Well, I wouldn't say the data set. I would say like how many updates you would need. Like how many gradient descent update you want. Like how many these operations, like you update of W, you will need. What? Through network? Yes. Okay. Any other question? Okay, so I will help to give you some kind of sense about the pros and cons about the stochastic gradient descent, right? For the gradient descent, of course, because every time you're calculating the accurate gradient, when the number of training examples is small, you probably need just a few iterations to converge. But for stochastic gradient descent, the number of iterations is large, right? But things will change in big data. Like consider you have billions of training examples, then the number of gradient descent you would require to converge will be much larger. That's the major issue. Okay, so the last thing about this SVM training is some kind of interesting comparison to perceptron. Right? So if we take a look at this whole framework, so this is very important. I hope everyone understand this framework clearly because you're gonna implement this one in our next homework. Right? So we initialize our model parameters as 0. Then we go through big T epochs. Of course, big T here is a hyperparameter. You need to decide by yourself, right, according to particular problem, right? And then for each epoch, we're gonna random shuffle the training set. Then we'll go through every training example, right? And then we take a look at, okay, if our functional margin, which is the product between yi and w transpose xi, less than or equal to 1, I'm gonna update the w with this subgradient, right? Otherwise, I'm gonna update w with another subgradient. Right? This is what we have derived for the subgradient. Right? So now let us recall, what does perceptron do in the update? So we could see that, okay, the outer operations, all in outside are all the same, right? The only difference is how we update W when we process each example, right? This is a perceptron, right? We just look at if we're making an example, making a correct prediction, right? If the prediction is correct, then we don't update W. In other words, we can view like we add 0 or we minus 0 to W, right? But if we make mistakes, which can be checked or verified by this inequality, then we update W by using this guy, right? Namely, W equals to W plus R yi xi. Right? This is a perceptron updating rule. So we see that, okay, looks like the whole framework is the same, right? SVM and perceptron. The only difference is at how we're going to update the model parameters every time when we see an example. So now the SVM update can be viewed as, running some stochastic subgradient to minimize some loss function, right? Can we think back about perceptron, right? is the perceptron update corresponding to another type of loss. In other words, if there is some kind of loss such that the perceptron update is just performing some kind of stochastic subgradient to minimize that loss. Right? Any thought? Anyone think about if you can find any like potential or implicit loss function that perceptron is actually minimizing? Any thought? Okay, so actually, it's not very hard to construct such implicit loss function for perceptron, right? So if we write down a loss in terms of like this, right? As maximum between 0 and minus YW transpose X, we'll see that if you perform sub gradient descent, you're going to recover exactly the perceptron updating rule. Okay. Let's try to verify, right? So, okay. So first, when is this max is 0? When this prediction is correct, right? Well, let's be more a little bit more detail. Like, if it is 0, that basically means this guy must be less than 0, right? That basically means like Y times W transpose X must be no less than 0, right? This just tells us you are making a correct prediction. When you are making a correct prediction, the subgradient is simply 0, right? Because your maximum between 0 and this guy is 0, right? So when you calculate subgradient 0, you use 0 to update your model. Actually, you are not updating your model. Okay. So that's for the first case in the perceptron update. If your model can correctly predict the current example, you won't need to update the model. Okay, let's consider another case, right? When the max between 0 and minus YW transpose X equals to the latter term. Of course, when this guy, this function margin less than 0, right? In this case, that means you're making a wrong prediction, right? And then if we calculate subgradient, we can just calculate the gradient of the second term, right? What's the gradient of the second term with respect to W? What's the gradient? Remember, this is just the dot product between W and X, right? If you want to calculate the gradient with respect to W, what's that? Yeah, it's just X, right? And times Y, right? So in this case, right, in the second case, where you are making a wrong prediction, then your subgradient will be just the gradient of the second term, which is simply Y times X, right? Now, if we apply this subgradient, right, to update our model, so basically means that we're gonna subtract W by this subgradient times some learning rate R, right? So you see that it turns out to be W plus R learning rate times Y times X, right? So you can see that this updating is exactly the same as the perceptron update when you make a wrong prediction. Right? Any question? So now we get an important insight. Actually, the perceptron, right? When we started discussing about it. It sounds like, okay, some like very smart guy and coming out some like nice heuristics to update the model, right? And we have explained the rationality of doing such kind of updates, both like, algebraically and also geometrically, right? It does show some like a sense, right? But now we have like even more rigorous justification. This update turns out to be optimizing some kind of loss function, right? This loss function is similar to hinge loss, but the difference is that, okay, it's also max between 0 and something, right? But the second term doesn't have 1 as compared with the hinge loss used in SVM. And an additional difference is that doing perceptron, we actually never consider some regularization term, right? For SVM, we have some regularization term, which is half W transpose W, then plus this hinge loss term, right? But for perceptron, first, we don't have the regularization term. Second, in our loss term, we don't have this extra constant 1. That's the difference. Okay, so hopefully this kind of comparison can bring us a better insight and also connection between these two learning algorithms. Remember, these two learning algorithms are both used for learn linear classifiers, but they are based on completely different principles. And those principles can be reduced to, or can be reflected into the design of the objective function. Okay. So we would like to summarize SVM from the optimization perspective. So the training of SVM is converted into minimizing a regularized hinge loss. Right? So in our loss, right, we have a regularization term which kind of encourage large margins and penalizing over complicated hypothesis, right? And plus a hinge loss, which kind of like evaluate how well you fit data. And we can solve this regularized hinge loss optimization problem while stochastic subgradient descent, right? The benefit includes like very fast, runtime does not depend on the number of training examples. And compare with perceptron algorithms, we found a surprising connection, right? They actually follow the same framework, but the perceptron just uses different objective function. In other words, like perceptron does not maximize the margin, right? And in addition to this simple stochastic subgradient descent framework for SVM training, there are other very successful and widely used optimization algorithms, which we do not have time to introduce. But that like linear, right? But that one needs a little bit more knowledge about dual coordinate descent. So any questions so far? Okay, great. So now we're gonna start talking about nonlinear SVM. So far about support vector machines, we haven't talked about how we derive the training principle, right? It is all started from the generalization error bound based upon the agnostic learning setting and the VC dimension, right? And it gives us like sense that, okay, why maximize margin can help us tighten the generalization error bound. Then we formulate the SVM objective function to maximize the margin. We do some kind of like a simplification about this objective function. We reduced our regularized hinge loss objective, right, in the SVM training. Right? Then we'll talk about like simple stochastic subgradient algorithm for optimization. Right? So, but all of those are talking about viewing support vector machines as just an ordinary linear classifier. Right? But when you use support vector machines, right? Like people by default assume it as a very powerful nonlinear classifier, right? So why is that, right? What I'm missing. So the remaining discussion about this topic is to address this question. So we're gonna first introduce another formulation of support vector machines, which is called dual form. It is completely derived based upon some basic optimization knowledge, which we'll have to introduce to everyone, right? Then we'll see that by using dual form, it is very easy to lift the capability of the SVM to do nonlinear classification. And the majority tool the major tool we're gonna leverage is called kernels or kernel trick, right? And we'll see like what are nice properties of kernels and why should we use kernel trick. And you see that directly apply the kernel trick to the dual form of SVM can lift their SVM to capable nonlinear classifiers. And also in the dual space or in the dual form SVM, by looking into the solution structure, we'll understand why SVM is called SVM. Right? More specifically, what does it mean for support vectors? Right? It's a weird name, right? Why we just don't call it another linear classifiers? Why we should call it support vector machines? Right? Where does this support vector come from? We'll address those questions. Okay. So far we have seen like support vector machines definition, hinge loss, and optimization, right? And those algorithms are just an alternative perception to learn a linear classifiers. And naturally, we want to extend our model to be a nonlinear classifier model, right? So we actually have discussed how to do this. If anyone could recall, right? A very intuitive way to lift the capability of linear classifiers that, okay, if in the original data space, the data set is not linear separable, so why not we just come out a feature mapping, a kind of smart feature mapping, which can map the instance in original feature space to some different space. And usually it will be in a higher dimensional space. In this higher dimensional space, we expect that those instances can be separated by some hyperplanes. That's the idea, right? So in this case, like for this data points, right? The blue squares and the red circles, of course, they're not linearly separable in our original space. And we can come out trick, right? We transform every input instance into a 4-dimensional feature vector. The idea is pretty simple, right? The original feature vector will be x1, x2. And then I take the square of each feature and append them to the feature vector. So got a 4-dimensional feature vector, x1, x2, x1 square, and x2 square. And you will see that by doing this kind of feature transformation in this new instance space, 4-dimensional instance space, it will be very easy to find a separating hyperplane which perfectly differentiate positive examples and negative examples. Okay. If we write it out, right? If we write it out, it's like, okay, I'm gonna first come out some kind of feature mapping file. Like for x1, x2, I convert it into a 4-dimensional feature vector. Then in this 4-dimensional space, I'm trying to find out a linear classifier such that this linear classifier can correctly predict the labels of all the positive examples and negative examples. So that's the idea. Any question? So later we're going to talk about how do we fulfill this idea in SVM framework. But before that, we need to introduce a little bit fundamental knowledge about optimization, which is called primal form and dual form for constraint optimization. Okay, So let us consider a primal problem. The primal problem is usually described as a general constraint optimization problem. So suppose this is our objective function f. We want to minimize f, but subject to a list of constraints. Each constraint is described by an inequality, like g1x less than equal to 0, g2x less than equal to 0, until gm of x less than equal to 0. Okay. So this is defined as the primal form. So to analyze this problem, right? Maybe you haven't heard of this term before. Right? We can construct an augmented function, which we call Lagrange form. So the Lagrange form is simply the objective function plus a linear combination of the constraint function. And the coefficient for every constraint function is called a Lagrange multiplier. I believe everyone has seen this term before, right? Like in our, I don't know, high school or in the first year of college calculus, right? So if we could remember, right, we learn how to solve a constraint, equality constraint optimization problem, right? The basic formulation is that, okay, I'm gonna use Lagrange form, right? And then I just take the gradient of Lagrange form and solve this gradient being 0, I can solve the constraint optimization problem, but with equality constraints. Does it make sense? Right? But here we're going to talk about a more general situation. So it's not necessary to be an equality constraint. In general, it is like inequality constraints. But if we want to impose some equality constraints, right, we can put it constraint like g1x less than equal to 0 and g1x bigger than or equal to 0. That actually induce the equality constraints. Any question? Okay. So let us proceed, right? So usually optimizing a objective function f, and meanwhile we have to consider this x must satisfy like m constraints. This is kind of like a very hard problem, right? It's not very easy to deal with. It's not very easy to analyze, right? So people will consider converting this primal problem into an equivalent minimax optimization problem. So basically, we claim that this constraint optimization problem, also called the primal problem, is equivalent to solving a minimax problem over the Lagrange function. So you can see that now in the minimax optimization, the objective function is the Lagrange form. It's not the original objective function. The Lagrange form is f of x plus a linear combination of the constraint function. And we actually have a additional set of variables that needs to optimize, which are Lagrange multipliers, right? Lambda i's. Okay? And then this optimization is two-level. In the inner level, we're going to maximize the Lagrange function with respect to lambda. But here, we only require lambda to be non-negative. So you see that the constraints over lambda is very simple, right? It's usually much simpler than the general case like g1x to gmx less than or equal to 0. Then in outer level, we're going to minimize the Lagrange function with respect to x. X, the original variables we want to optimize. Okay. And for simplicity, we're going to write this minimax optimization problem in this form. Right? We're going to conduct minimax optimization over the Lagrange form, Lx lambda, such that in the inner level, lambda must be non-negative, and we want to maximize L with respect to lambda. And in the outer level, we're going to minimize L with respect to X. But here, X is unconstrained. You don't need to consider like whether X should satisfy any constraints. Is everyone clear about this formulation? Before we talk about why this is equivalent. Everyone's comfortable? Okay, so now let us explain why this general constraint optimization problem can be converted into an equivalent minimax optimization. The benefit of minimax optimization is that, okay, first, we get rid of like complicated constraints, right? For X, there's no constraint. You don't need to worry about if X satisfies G1X, G2X less than or equal to 0, and so on, right? And for lambda, for this additional variables we introduced, you only need to pose a non-negative constraint, which is much easier. Okay, then why? They are equivalent. We can find the equivalence through a little bit of analysis. So let us consider we have some X fixed outside, right? Remember, this is a minimax optimization, right? We can consider like we have some fixed X here in the outer side and just look at what is the optimization results in the inner level. In the inner level, actually, we're trying to maximize the Lagrange function with respect to non-negative multipliers lambda, right? So we actually have two cases. If X in outer level, which is now fixed, right, has already satisfied all the constraints, meaning that G1X is less than 0, G2X less than or equal to 0 until Gmx less than or equal to 0, then what's the maximum value of this Lagrange function with respect to lambda? What's it? Y must be 0. Yes, exactly, right? So in the first case, let us assume the X we fixed in the outer level has already satisfied these constraints. That means like when you evaluate every constraint function, they are negative, right? Now I want to maximize the whole Lagrange function. I have no choice. I have to set all lambda i's to be 0, right? Otherwise, you're gonna subtract some number, right? You're gonna decrease the value. So in this case, the maximum is achieved when you set all lambdas to 0. And all lambdas to 0, that basically means like these summations are 0, right? Then your maximum value is just f of x. That's situation 1, right? So for situation 2, if in outer level, the fixed x does not satisfy all the constraints, right? At least it violates one constraint. Like say some GIX is bigger than 0. Then what's the maximum value can we get from maximizing the Lagrange function? Suppose our X has violates like ith constraint such that, GIX is bigger than 0. Now, if we consider what's the maximum value of this Lagrange function, how would we choose the corresponding lambda values? Y is infinite. Yeah, exactly, right? So we don't need to consider other things, right? Just consider one case, like suppose for constraint I, X violates the constraint I. That basically means GIX must be bigger than 0. So now you multiply lambda I with GIX, right? You have the flexibility to tune lambda to be positive, right? Of course, I want to maximize the function, right? I can make lambda as large as possible. Actually, you can make lambda I to be infinity, right? that means the whole Lagrange function will be infinity as well. Does it make sense? Right? And then it basically tell us like two situations. Like first, if in outer level, the X has satisfied all constraints, then the maximum of this Lagrange function will be reduced to the original objective function, f of x. Otherwise, if x violates any constraints, then the maximum of Lagrange function goes to infinity, goes to unbounded. And remember, our goal is to minimize in outer level, right? Our goal is to minimize the whole thing in the outer level. The only feasible things which give us the minimum will be the set of x which satisfy the constraints, right? Otherwise, if x violates any constraint, the inner level will give you infinity, right? Of course, infinity is bigger than anything. So the minimum is only obtained when you search over those x who satisfy all the constraints, right? And when you search those x who satisfy all constraints, it is equivalent to search the minimum of the original objective f of x, which satisfy all the constraints. In other words, it is equivalent to solving the original constraint optimization problem. Does it make sense? Yeah, if you feel uncomfortable, that's fine. Because this is kind of like very smart design. But you see that if you try to really conduct some kind of optimization from the inner level and then proceed to the outer level, you see this whole procedure is equivalent to searching all x which satisfy the constraints and then minimize the original objective function. It is equivalent. But the benefit is that if we formulate in this way, you are not explicitly constraining x. Okay? And you only put a non-negative constraint over lambda. So that's the benefit. Okay, any questions so far? Okay, so to help us to better understanding this whole formulation, I will leave an exercise for you. Right? Suppose now I want to change my constraint, not be like this. Right? I want to change my constraint to be exact equality constraints. Suppose I have m constraints, okay, where each constraint is represented by an equality. G1x equals to 0, G2x equals to 0, until Gm of x equals to 0. Then my question is that, how do we construct an equivalent min-max optimization problem? Try to think about that. It might be included in our next homework. And if you can work out it, that means like totally understand this framework. Okay. Any questions so far before we proceed? Okay, great. So without loss of generality, we're going to use this min-max formulation to represent our primal problem, because the primal problem is equivalent to this min-max optimization problem, right? So then the next concept is called dual form. What does it mean for dual form? We simply switch the order of the optimization. And that is, we're going to first minimize the Lagrange function with respect to x, And then in the outer level, we maximize the Lagrange function with respect to non-negative multipliers lambda. This is called dual form. So it's the same as primal form. The only difference is you're going to switch the order of the optimization. So now I want to ask, are the solutions of dual form and primal form the same? In other words, does the switch of this optimization order will affect the solution? Any guess? Just give me a guess. It would. Why would why would it affect? Yeah, your intuition is exactly right. If it doesn't affect, why should I ask this question? Right. So in general, like when you switch the order of max and min, it will affect the solution for sure. And here is the conclusion. The conclusion is that if you look at the solution of the dual form, right, you evaluate your objective function, which is Lagrange function here, right? Your function evaluated at the optimum of the dual problem will be less than or equal to the function evaluated at optimum of the primal form. And it's very famous and very fundamental conclusion in the optimization theorem. If you have taken any optimization class, you should have heard of this concept before, right? People often call like dual form is a lower bound of the primal form, right? And it's pretty easy to show this, right? But I'm not gonna go through the details because it's not required. But we have listed the proof steps, right? If you're interested, you can go through those steps. It's just two or three inequalities. You connect them together, and it's very easy to show that actually the objective at the dual solution is upper bounded by the objective at the primal solution. But here, we want to emphasize we're lucky because we're dealing with SVM. In the SVM context, dual form is equivalent to the primal form. In other words, solving dual form will end up with the same solution as solving the primal form. And why do we introduce dual form? Right? I will explain later. Right? When we switch the order of this minimax of procedure, we first do min and then do maximization. And when we try to solve it, you're going to find a lot of interesting conclusions. And if you apply these interesting observations into the objective formulation, you'll get very succinct and meaningful form of your new objective, which now allow you to apply the kernel trick and to perform nonlinear classification, but also give you a lot of other meanings. Right? This is our discussion in the next step. Right? Okay, so now let us look at the primal form and dual form for SVM and see what kind of interesting thing can we find by solving the dual form. Right? So first, this is the primal form. Right? Remember, this is our formulation of soft SVM. Right? Our objective is the square of the half of the square norm of W plus a summation of a set slack variables. And the C here is a positive constant, which indicates the trade-off between the large margin principle and data fitting, right? By the way, what does KCI mean here? Anyone recall? What does KCI mean here? Why would we introduce KCI here? That really is how we formulate the problem, right? So in a general case, we can't assume the data set is always linearly separable, right? And so that's why we introduced soft SVM, which will allow some examples to be to break into the margin, right? To intrude the margin. To allow our algorithm to automatically find out which examples can intrude margin. We introduce this slack variable KCI, right? If KCI equals to 0, that basically means your function margin is no less than 1. It means that example, xi, stay on the margin or outside margin. If KCI is absolutely bigger than 0, right? Say 0.5, right? Then that means your functional margin could be less than 1. That, like this example, right? This example. Then that means like this example is allowed to break into the margin. Right? That's how we formulate soft SVM. And the reason we put the summation of those slack variables KCI in the objective is we want to avoid as many examples to break into the margin as possible, because we don't want so many examples to break into the margin, because that will cause your training error to be large, right? And the generalization error bounds is determined not only by the VC dimension, but also by the training error, right? If your training error is too large, your generalization error bound will be large as well. Okay? That's why we claim that, okay, this guy indicates kind of like controlling of the training error, and this guy indicates the regularization, the VC dimension stuff. And then we want to minimize this whole objective with respect to model parameters, that is width vector, feature width vector W, the bias parameter B, and this set of slack variables. And remember, for every training example I, we have two constraints here. First, the slack variable must be non-active. And second, the function margin must be no less than 1 minus KCI. Okay. Are we on the same page? This is a quick review of our soft SVM formulation again, right? Okay, so next thing is quite mechanical. We're gonna apply the primal and dual form we just introduced to our SVM objective, right? So let me erase those guys. So see that for every training example, we actually have two constraints, right? One constraint is about the functional margin. The function margin should be no less than 1 minus KCI. Okay? So correspondingly, we can introduce a Lagrange multiplier for this constraint, which we denote as alpha I, right? And the second one is the non-negative constraint about KCI. And we can introduce another multiplier beta I, right? And remember, in the standard primal problem formulation, we require the constraint to have the form like J x less than or equal to 0, right? So we need to turn off, we need to switch the direction. We need to revert the direction of the inequalities, right? And then we just add the objective function by the linear combination of those constraint functions. Each constraint is multiplied by the multiplier alpha I, beta i's. We end up with our Lagrange function. Does it make sense? Right. And then we know that in the minimax formulation, in the inner level, we need to maximize the Lagrange function with respect to the multipliers. Here we have two types of multipliers, alpha i's and beta i's, remember, right? Alpha i's are for those function margin constraints, and beta i's are for the non-negative constraints of Ci. And then in the outer level, we minimize the Lagrange function with respect to WB and those slack variables. This is just a straightforward application of the primal form and the Lagrange form. Right? And then by switching the max and min order, we arrive at the dual form of SVM. In the inner level, we're going to minimize this lengthy objective function with respect to the model parameters WB and the slack variables for Ci's. Then in the outer level, we maximize the Lagrange function with respect to the multipliers alpha i's and beta i's. Again, this is just following the definition. Right? And as to why doing this order switching won't change the optimization results, it comes from some famous theorem in convex optimization. So basically, if you're solving a convex optimization problem, and if you satisfy this so-called Slater's condition, then primal form and dual form are equivalent. And basically what does it mean for Slater's condition? Well, I won't introduce the details, but give you a sense that the Slater conditions requires that your feasible region, by feasible region, it means like the set of variables, optimization variables, which satisfy the constraint. It just means that the domain, the feasible domain must have at least one interior point, right? And mean that, like, imagine like you have some domain like internal, there are at least one internal point, then the dual form is equivalent to the primal form. If all the points stay on the boundary, then it doesn't have such a conclusion. Okay, so now let us look at the dual form of SVM and see how can we simplify this problem. So we have already known like doing max min is equivalent to solving the original SVM, right? But we don't really want to do max min optimization, this two-level optimization problem. Right? We want to simplify it. How do we simplify it? We can do it step by step. Right? So let us consider in the outer level, we have some alpha i's and beta i's there. Then we directly solve the inner level, which is minimizing the Lagrange function with respect to the model parameters and slack variables. How can we do that? How can we do that? Yeah, we just take the gradient and set the gradient to be 0 and see what we can get, right? So we have three variables, right? The feature weight vector W, the bias parameter B, and also the slack variables for every training example, right? Then we just take gradient of our Lagrange function L with respect to all of them and set the gradient to be 0. And through some kind of like simple algebra, you find that setting the gradient with respect to W to be 0 and solve it, you can get W equals to this guy. You see that W equals to a linear combination of every training instance. Okay? And multiply with alpha i's. Okay? Alpha I, remember, it is a Lagrange multiplier. So it's a Lagrange multiplier. Alpha i's who combine xi, y's together to give our optimal W. And solving the gradient with respect to B being 0, you can get an equality, which says the summation of all alpha I or i's equals to 0. Why do you get this? Because you see that the B term is actually a linear term, right? If you take the gradient with respect to B, the B disappears, right? That basically means you want the total coefficient for B to be 0, which gives you this, right? And third one, if you take the gradient of L with respect to Ci and set the gradient to be 0, you get this interesting result. it basically says your alpha I and beta I, the summation must be C. And what is C? Observe that C is here, right? The hyperparameter C is kind of a trade-off between the regularization and the slack variables, right? If you take a look here, right? This is where we have C, right? Okay, so now let us substitute those results back into L and assume that, okay, we are able to solve the inner minimization problem. Let's see what happens, right? If you substitute them into L, you got a much simplified form for your objective function, which is this guy. I'm not gonna derive it like in detail, but you can definitely verify this by yourself. Right? We see that in this new objective, right, you got a quadratic form. You're gonna just multiply every combination, every pairs of combination of yi, yj, and alpha I, alpha j, and the dot product between the feature vector x and j, and plus the summation over alpha i's. So this is the optimal results of the inner minimization. Then the only thing you left is to maximize this guy in the outer level with respect to the Lagrange multipliers alpha i's, betas. Right? And meanwhile, we should be aware that this optimal inner minimization results is obtained if and only if this three gradient to be zero, right? That means if you want to use the result here as your new objective, you must make sure all of these three are satisfied. And this guy has already been substituted into L, so it is automatically satisfied. But these two are not explicit. So that means like in your simplified objective, you have to explicit put them into the constraints. And eventually, you have converted our dual form of SVM into a maximization problem, right? And with two additional constraints. Any questions so far? Okay, then there are some like a remaining some kind of further simplification, right? So first we observe that in the objective function, you actually does not contain beta, right? And but here we only need to constrain beta I no less than 0, and we have a equality constraint such that alpha I plus beta I equals to C. So equivalently, we can just get rid of beta I and then require alpha I to be less than or equal to C, right? Because beta I from this constraint means that beta I is always C minus alpha I, right? If alpha I less than or equal to C, that means this constraint is automatically satisfied. So we can do some further simplification. And also, you know, we kind of like negate the objective function, meaning that we're going to do minimization, right? And eventually we reduce our dual form into a quadratic optimization in this form. So in this objective, in this quadratic form, we have this, in this quadratic optimization problem, we have this quadratic optimization function with respect to alpha i's. Those are only for Lagrange multipliers, right? And also summation of alpha I. And but we need to respect the two constraints. First, two types of constraints. First, for every alpha I, it should be between 0 and C. And second, the summation of all alpha I yi's must be 0. Then we have derived the dual form of SVM. Right? And the whole derivation procedure is kind of like tedious, but it's actually pretty simple at every step. Right? We just construct the primal form of the original soft SVM formulation, and switch the order of max min, we get dual form, right? And then we try to simplify the dual form by fixing the outer level and solving the minimization problem in the inner level, you get some results, right? You just substitute those results back into the objective function, you get a simplified objective function and additional constraints. That means you just need to solve and maximize optimization in the outer level with respect and respecting those constraints. And finally, you do a little bit further simplification, you end up with our final dual form of SVM. Right. So, and the nice property of this dual form is that, okay, first we can just apply the standard quadratic convex optimization package to solve that problem. You don't need to solve it by yourself. Second, as we'll see in the next lecture, this form allows us a straightforward application of so-called kernel trick. Basically, you can replace the dot product between every pair of xi and ig by some kernel function. Then the SVM is automatically lifted in the latent high-dimensional feature space to perform nonlinear classification. So let's continue the discussion on next Tuesday. See you on next Tuesday.